Have you ever stopped to think about what you're actually sitting on right now? Not the chair, not the floor, not the earth beneath your feet, but something far more fundamental. The fabric of reality itself. The invisible structure that holds everything together, that gives meaning to the words here and there, now and then, that makes it possible for you to exist in one place at one time and nowhere else. We call this fabric space-time, and it is without question one of the most profound and mysterious concepts in all of human knowledge. You've heard the word before. Scientists use it constantly. Einstein's theory of space-time, the fabric of space-time. Space-time is curved, ripples in space-time. The words flow smoothly in documentaries and textbooks and popular science articles, as if everyone knows what they mean, as if the concept is settled and understood. But here is what most people never realize, what most science communicators gloss over in their rush to get to the exciting stuff about black holes and wormholes and the Big Bang. When you actually dig into what space-time means at the deepest level, when you push past the equations and the analogies and the beautiful metaphors and ask the most basic question of all, what actually is it? You discover something deeply unsettling. We don't know. We genuinely, honestly, completely do not know. We use this idea every single day. Your GPS wouldn't work without it. We've photographed the warping of space-time around black holes. We've detected gravitational waves, ripples propagating through the fabric of space-time itself, created by colliding black holes more than 1 billion light-years away. We can calculate the curvature of space-time around any mass to extraordinary precision, and those calculations predict observations that match reality with mind-bending accuracy. And yet, we have no idea what space-time actually is at its most fundamental level. We know how it behaves. We can predict what it does. But we cannot tell you what it's made of, whether it's made of anything, whether it's truly fundamental, or whether it emerges from something deeper and stranger that we haven't discovered yet. This is not a small gap in our knowledge. This is not a minor technical detail waiting to be filled in by the next generation of physicists. This is one of the central unsolved mysteries of all science. It sits at the intersection of the two greatest theories ever developed by the human mind, general relativity and quantum mechanics, and those two theories cannot both be right in their current forms. They contradict each other at the deepest level. They make incompatible assumptions about the nature of reality. And the place where they contradict each other most violently is precisely the nature of space-time itself. By the time we're done tonight, you're going to understand this mystery in a way that most people never do. You're going to understand not just what space-time is supposed to be and how it works in the theories we have, but why those theories are incomplete, what they can't explain, and why solving the mystery of space-time might be the most important scientific achievement of the coming century. This is a story about the deepest nature of reality, and it begins as so many great stories in physics begin, with a young man thinking strange thoughts about light. Let's go back to 1905. Albert Einstein was 26 years old. He was living in Bern, Switzerland, working as a patent examiner, third class, at the Federal Office for Intellectual Property. He wasn't a professor. He wasn't attached to a university. He had graduated from the Zurich Polytechnic 4 years earlier, but had been unable to secure an academic position afterward. Some of his professors found him difficult, too independent, too challenging of received wisdom. One professor, Heinrich Weber, who might have been expected to provide a recommendation that would help Einstein's career, reportedly told him that he was clever enough, but had one serious failing. He refused to accept anything he was told. So Einstein ended up at the patent office, spending his days evaluating applications for electromagnetic devices and his evenings and weekends thinking about the deepest problems in physics. And in 1905, in what scientists now call his annus mirabilis, his miraculous year, he published 4 papers that would permanently alter the course of human understanding. The first explained Brownian motion, the random jiggling of tiny particles suspended in a fluid, and in doing so provided the most convincing evidence yet that atoms were real physical objects and not just a useful mathematical fiction. The second explained the photoelectric effect, showing that light comes in discrete chunks of energy called quanta rather than being a continuous wave. And this paper, not Relativity, would eventually win him the Nobel Prize because it was so fundamental to the emerging field of quantum mechanics. The third and fourth papers introduced special relativity, a complete overhaul of how physics understood space, time, and motion. Special relativity sounds intimidating, but the core idea is actually something you can state very simply. Einstein realized that the speed of light is the same for every observer, regardless of how fast they're moving. That's it. That's the starting point. Everything else flows from that single remarkable fact. But to understand why this is so strange, you need to understand what we normally expect when it comes to speeds and motion. Imagine you're standing on a train platform. A train goes past at 100 kilometers per hour. A passenger on the train throws a ball in the direction the train is moving at 20 kilometers per hour relative to the train. From your perspective, standing on the platform, that ball is moving at 120 kilometers per hour. The speed of the throw adds to the speed of the train. This is completely intuitive. This is how the world works at human scales. Velocities add together. This principle goes back to Galileo, and it was incorporated into Newton's mechanics. It's called the Galilean transformation, and for centuries it worked perfectly. Now, replace the ball with a beam of light. You're still on the platform. The train is moving at half the speed of light, about 150,000 kilometers per second. The passenger on the train turns on a flashlight and shines it forward. How fast is the light moving relative to you on the platform? If velocities add normally, you'd expect 300,000 kilometers per second plus 150,000 kilometers per second, giving you 450,000 kilometers per second. But that's not what happens. The light moves at exactly 300,000 kilometers per second relative to you, the same as it moves relative to the passenger on the train. This was not a theoretical prediction that Einstein just dreamed up. It was already known from experiments. In 1887, Albert Michelson and Edward Morley performed an extraordinarily precise experiment designed to measure how the speed of Earth's motion through space affected the speed of light in different directions. They built a device called an interferometer that split a beam of light into 2 perpendicular paths, bounced the beams off mirrors, and recombined them. If light traveled at different speeds in different directions due to Earth's motion, the interference pattern when the beams recombined would shift as the apparatus was rotated. They found no shift at all. The speed of light was the same in every direction regardless of Earth's motion. This result baffled physicists for nearly 2 decades. They tried to explain it by proposing that the ether, the hypothetical medium through which light was supposed to travel, was somehow dragged along by the Earth. They proposed that objects moving through the ether contracted slightly in the direction of motion, a hypothesis put forward independently by Lorentz and Fitzgerald. Various patches were tried, and none of them were satisfying, because none of them came with a coherent physical picture of what was actually happening. Einstein's approach was different. Instead of trying to patch up the existing framework, he asked a more fundamental question. What would the universe have to be like if this result was simply true? What would the world have to be like if the speed of light were genuinely the same for every observer? And when he worked out the consequences, he found that space and time themselves had to be flexible. They had to be able to stretch and compress in ways that Newton had never imagined. If the speed of light is the same for everyone, regardless of their motion, then as you move faster through space, time has to slow down for you. This is not a trick, not an illusion, not a perceptual effect. Time literally runs more slowly for moving objects. If you take two identical atomic clocks, set them both to exactly the same time, put one on a fast-moving jet aircraft and leave the other on the ground. When the aircraft lands and you compare the clocks, the one that flew on the aircraft will show that slightly less time has passed. This has been measured directly multiple times. The effect is small for aircraft moving at ordinary speeds, only a few hundred nanoseconds for a flight around the world, but it's real, it's measurable, and it matches Einstein's predictions exactly. At very high speeds, the effect becomes dramatic. If you could build a spacecraft that travels at 99% of the speed of light, time on that spacecraft would pass about 7 times more slowly than time on Earth. A journey that takes 7 years from Earth's perspective would only feel like 1 year to the crew. At 99.9% of the speed of light, the ratio is about 22 to 1. A year on the ship corresponds to 22 years on Earth. And as you push closer and closer to the speed of light, the time dilation grows without bound. At exactly the speed of light, time would stop completely. But nothing with mass can reach the speed of light, because another consequence of special relativity is that as you go faster, your effective mass increases, which means it takes more and more energy to accelerate you further. As your speed approaches the speed of light, the energy required to accelerate you further approaches infinity. And since you can never have infinite energy, you can never reach the speed of light if you have any mass at all. These were shocking conclusions in 1905. They overthrew 3 centuries of Newtonian mechanics, which had treated space as an absolute, fixed stage on which events played out, and time as an absolute flow, the same for all observers everywhere. Newton's physics had been so successful, had predicted the motions of planets and projectiles and pendulums and satellites with such extraordinary accuracy that most physicists took it as essentially the final word on mechanics. Einstein showed that Newton's picture was an approximation, accurate for slow speeds, but fundamentally wrong about the nature of space and time. The 2 papers on special relativity included one of the most famous equations in all of science, E equals mc squared, energy equals mass times the speed of light squared. This equation says that mass and energy are not separate things, but different manifestations of the same thing. A small amount of mass corresponds to an enormous amount of energy, because the speed of light squared is a very large number. 1 kilogram of matter, completely converted to energy, would release about 90 quadrillion joules, equivalent to roughly 21 million tons of TNT, about 2,000 Hiroshima bombs. This relationship is what makes nuclear weapons possible and nuclear power plants possible. When uranium or plutonium undergoes fission, a tiny fraction of the mass of the atomic nuclei is converted to energy. Einstein's equation tells you exactly how much, but special relativity revolutionary as it was incomplete. It only applied to objects moving at constant velocities. It didn't handle acceleration, and crucially, it didn't handle gravity. Newton's theory of gravity had been one of the greatest triumphs of human intellect, published in 1687 and used successfully to predict everything from the tides to the orbits of distant planets. But Einstein realized it couldn't be right, at least not completely. The problem was simple but devastating. According to Newton's law of gravity, the gravitational force between two objects depends on the masses of both objects and the distance between them, and it acts instantaneously. If the sun were to suddenly disappear, Earth would immediately feel the change and fly off into space. The gravitational information would travel from the sun to Earth in zero time, crossing 150 million kilometers in an instant. But Einstein had just shown that nothing can travel faster than light. No signal, no force, no information of any kind can cross space instantaneously. Whatever carries the gravitational force, whatever communicates the presence of a massive object to other objects far away, it can't move faster than light. This meant Newton's theory of gravity was fundamentally wrong, not just approximately wrong in extreme cases, but wrong in its basic picture of how gravity works. Einstein knew he had to replace it with something better, and he spent the next 10 years of his life doing exactly that. The result was General Relativity, published in November 1915, and it remains arguably the most beautiful physical theory ever constructed. The key insight that led Einstein to general relativity is something he later called the happiest thought of his life. He was sitting in the patent office in 1907 thinking about gravity when he imagined a worker falling from a roof. While the worker is falling, Einstein realized the worker doesn't feel their own weight. They're weightless. They're in free fall. If they dropped a hammer, the hammer would float beside them, both falling at the same rate. The worker would be unable to tell from any experiment they could perform in that brief falling moment whether they were in free fall near the surface of the Earth or drifting in empty space far from any gravitational source. Einstein recognized this as a profound truth. Being in free fall is physically indistinguishable from being in zero gravity, and being in an accelerating rocket ship in empty space is physically indistinguishable from standing on the surface of a planet, feeling gravity pull you down. If you're sealed in a box with no windows, and you feel a force pushing you toward one wall, you cannot determine by any experiment whether you're sitting on a planet's surface with gravity pulling you toward the floor or accelerating through empty space with a rocket pushing you from behind. The effects are identical. This principle that gravity and acceleration are locally equivalent is called the equivalence principle, and it became the foundation of general relativity. Now here's why this matters for spacetime. Special relativity had shown that acceleration affects time, that a clock on an accelerating spaceship runs slower than a stationary clock. If gravity and acceleration are equivalent, then gravity must also affect time. Gravity must make clocks run slower. A clock deep in a gravitational field, close to a massive object, must run more slowly than a clock far from any mass. This is called gravitational time dilation, and it's been confirmed by hundreds of experiments. The clocks on GPS satellites, which orbit at an altitude of about 20,000 kilometers, run faster than clocks on Earth's surface because they're farther from Earth's center and experience weaker gravity. Engineers have to correct for this effect continuously. Without those corrections, GPS would be useless within hours. But Einstein went much further than just predicting that gravity slows clocks. He realized that if acceleration and gravity are equivalent, and if acceleration curves the paths of light and objects through space, then gravity must do the same thing. Mass must curve the paths of light and objects, and if paths through space and time are curved, then space and time themselves must be curved. Gravity is not a force pulling objects together. Gravity is the curvature of space-time caused by mass and energy. This is a complete rewriting of what gravity means. In Newton's picture, the sun exerts a force on the Earth across empty space, pulling it toward the sun and keeping it in orbit. In Einstein's picture, there is no force. The sun's enormous mass creates a curvature in the fabric of space-time around it. Earth, moving through this curved space-time, follows the straightest possible path, a geodesic, and that straightest possible path happens to be a curve that loops around the sun. We experience this curving path as the effect of gravity. The standard analogy is a rubber sheet. Stretch a flat rubber sheet taut and place a heavy ball in the center. The ball creates a depression, a curve in the sheet. Now roll a small marble across the sheet. Instead of traveling in a straight line, the marble curves toward the heavy ball because the sheet itself is curved. This analogy captures something real about general relativity. Objects following straight paths through curved space-time appear to be attracted to massive objects, but the analogy has serious limitations. The rubber sheet is two-dimensional, curving into a third dimension. Real space-time is four-dimensional, 3 dimensions of space and 1 dimension of time, and it doesn't curve into some additional higher dimension. It curves within itself, which is a mathematically well-defined concept, but essentially impossible to visualize. Also, the rubber sheet analogy seems to require gravity to work, since the heavy ball only dips down because Earth's gravity pulls it down. In the real universe, there's no external gravity making massive objects curve space-time. The curvature is what mass does to space-time by its very nature. To express these ideas mathematically, Einstein needed tools he hadn't learned in his university education. He turned to his friend Marcel Grossman, a mathematician, who introduced him to the mathematics of curved surfaces and curved spaces developed by Bernhard Riemann in the 19th century, and extended to higher dimensions by later mathematicians. This mathematical framework, called differential geometry or Riemannian geometry, provided exactly the tools Einstein needed to describe how space-time curves in response to mass and energy. The result, after 8 years of intense work, punctuated by false starts, mathematical errors, and blind alleys, was the Einstein field equations. In their most compact notation, they can be written as G equals 8 pi times T, where G is the Einstein tensor describing the curvature of spacetime, and T is the stress-energy tensor describing the distribution of mass, energy, momentum, and pressure. This compact notation is deceptive. The equation actually represents 10 coupled, non-linear partial differential equations, and solving them for any realistic situation is one of the hardest mathematical problems in physics. The equations say, in essence, mass and energy tell spacetime how to curve, and curved spacetime tells mass and energy how to move. The two are inextricably linked, each affecting the other in a complex dynamic feedback. Even empty space is not empty in general relativity. The geometry of space-time carries energy, and changes in that geometry can propagate as waves. Einstein's first triumph with the new theory came in explaining a long-standing puzzle about the orbit of Mercury. Mercury, the innermost planet, doesn't orbit the Sun in a perfect ellipse. The ellipse itself slowly rotates over time, so that the closest point of Mercury's approach to the Sun, called the perihelion, shifts slightly with each orbit. Over a century, This shift adds up to about 574 arcseconds, and most of it can be explained by the gravitational pulls of other planets. But 43 arcseconds per century remained unexplained by Newton's theory. Astronomers had known about this for decades. Some had proposed an undiscovered planet closer to the Sun, which they called Vulcan, was pulling on Mercury and causing the extra shift. But no such planet had ever been found. When Einstein calculated what his equations predicted for Mercury's orbit, he got exactly the right answer. General relativity explained the full 43 arcseconds per century discrepancy, with no free parameters, no adjustments, no additional hypotheses. The theory just worked. And Einstein later said this discovery gave him heart palpitations when he realized what the equations were telling him. But the most dramatic confirmation of general relativity came in 1919. Einstein's theory predicted that light passing close to the Sun would be bent by the Sun's gravitational field, or more precisely, by the curvature of spacetime around the Sun. The bending it predicted was twice what Newton's theory predicted, because in Newtonian gravity, you can calculate a bending of light if you treat photons as having an effective gravitational mass, but you miss the contribution from the curvature of space itself. General relativity accounts for both effects and predicts exactly double the Newtonian value. To test this prediction, you needed to observe the positions of stars near the Sun. But normally you can't see stars near the Sun because the Sun's light overwhelms them. The only time you can is during a total solar eclipse, when the Moon blocks the Sun's disk and the sky briefly darkens enough to see stars that would otherwise be invisible. On May 29, 1919, a total solar eclipse was visible across a path that included the island of Principe off the west coast of Africa and a location in Brazil called Sobral. The British astronomer Arthur Eddington led an expedition to Principe, and a second British team went to Sobral. Both teams photographed stars near the Sun during the eclipse. They compared these photographs to photographs of the same stars taken months earlier when the Sun was in a different part of the sky, so the stars could be photographed at night without any solar interference. The stars near the Sun during the eclipse appeared shifted from their expected positions, shifted by exactly the amount Einstein had predicted. Light had been bent by the Sun's gravity, and it had been bent by exactly twice the Newtonian value, exactly as general relativity required. When the results were announced in November 1919 at a joint meeting of the Royal Society and the Royal Astronomical Society in London, the physicist J.J. Thomson, who had discovered the electron, declared that Einstein's theory was one of the greatest achievements in the history of science. The next day, newspapers around the world ran the story. Einstein became an international celebrity overnight, the most famous scientist in the world, a status he would maintain for the rest of his life. He was photographed, interviewed, invited to lecture everywhere. People who had never heard of relativity before were suddenly fascinated by this man who had shown that light could be bent by gravity, that space and time were flexible, that the universe was a stranger place than anyone had imagined. The years following the 1919 eclipse brought more confirmations of general relativity. Astronomers observed gravitational lensing, the bending of light from distant galaxies by massive foreground objects, creating arcs and rings and multiple images of the same source. They observed gravitational redshift, the stretching of light's wavelength as it climbs out of a gravitational field which had been predicted by Einstein and was confirmed experimentally in 1959 by Robert Pound and Glenn Rebka in an elegant experiment performed in a tower at Harvard University. They observed the slowing of radar signals passing close to the Sun, an effect known as the Shapiro delay after its discoverer, which was confirmed in the 1960s. Each of these tests confirmed general relativity to extraordinary precision. The theory was not just approximately correct. It was correct to many decimal places, matching observations better than any other theory of gravity ever proposed. By the middle of the 20th century, general relativity was as firmly established as any theory in physics. It was the accepted framework for understanding gravity, cosmology, and the structure of the universe at the largest scales. But even as general relativity triumphed, it contained within itself the seeds of the deepest problems in all of physics. Almost immediately after Einstein published his field equations in 1915, physicists began finding solutions to those equations that described extreme situations so extreme that the mathematics began to break down in disturbing ways. The first solution was found not by Einstein himself, but by a German physicist named Karl Schwarzschild, who was serving in the German army on the Russian front during World War I. Despite the brutal conditions of the war, Schwarzschild worked on physics during whatever spare moments he could find. He solved Einstein's equations for the simplest possible case, a perfectly spherical, non-rotating, uncharged mass sitting alone in empty space. This solution, which he sent to Einstein from the front in December 1915, just weeks after Einstein published the field equations, described how spacetime curves around a star or planet. The solution worked beautifully for the space outside a massive object. But Schwarzschild noticed something peculiar in the mathematics. At a certain distance from the center of the mass, the equations behaved strangely. Certain quantities became infinite. The mathematical description broke down. This critical distance became known as the Schwarzschild radius. For any object, you can calculate its Schwarzschild radius by dividing its mass by a constant. The Schwarzschild radius of the Sun is about 3 kilometers. The Schwarzschild radius of the Earth is about 9 millimeters. At the time, this seemed purely mathematical. The Sun is much larger than 3 kilometers across, so the weird behavior in the equations only occurred deep inside the Sun's material, where Schwarzschild's vacuum solution didn't apply anyway. Similarly, the Earth's Schwarzschild radius was deep inside the Earth. So the singularity, as it came to be called, seemed like a mathematical artifact, a flaw in the solution that had no physical significance. Schwarzschild himself died just a few months after publishing his solution. He had contracted an autoimmune disease while on the front and died in May 1916 at the age of 42. He never knew that his mathematical curiosity would one day be recognized as one of the most important concepts in all of physics. For the next several decades, most physicists treated the Schwarzschild singularity as Einstein did, a mathematical oddity, not a physical reality. If you somehow compressed any object to within its Schwarzschild radius, the equations predicted something bizarre. Spacetime would curve so strongly that light itself could not escape. Any object inside this critical radius would be trapped, unable to communicate with the outside universe. A black hole, though that term wasn't coined until 1967, had been lurking in the mathematics of general relativity from the very beginning. Einstein was disturbed by this implication. He wrote a paper in 1939 arguing that such objects could never actually form in nature. He believed that some physical process, some pressure or force, would always prevent a star from collapsing past its Schwarzschild radius. The singularity was not a prediction about reality. It was a signal that the equations were being pushed into a regime where they weren't valid. And then in 1939, the same year Einstein wrote his paper J, Robert Oppenheimer and his student Hartland Snyder published a calculation that showed exactly the opposite. They modeled a massive star that had exhausted its nuclear fuel and could no longer support itself against its own gravity. They showed mathematically that such a star would collapse completely. There was no pressure, no force, no quantum effect strong enough to stop it once it began. The star would shrink past its Schwarzschild radius and continue collapsing until it reached a singularity at the center, a point of infinite density where the equations of general relativity stopped making sense. Oppenheimer and Snyder's work was largely ignored for decades. The Second World War intervened, and after the war, the scientific community was preoccupied with other things, including the development of nuclear weapons and the beginnings of the quantum field theory program that would eventually become the standard model of particle physics. Black holes remained a theoretical curiosity, but observations began to force physicists to take them seriously. In the 1960s, astronomers discovered quasars, objects that radiated enormous amounts of energy from tiny regions of space. The most luminous quasars outshine entire galaxies by factors of hundreds or thousands, yet vary in brightness on timescales of days or weeks. Since nothing can travel faster than light, the region producing the radiation can be no larger than the distance light travels in the time of the variation. That meant these incredibly luminous objects were also incredibly compact. The only physical mechanism anyone could devise to produce such enormous energies from such small volumes was accretion, material falling into a supermassive black hole and releasing gravitational energy as it spiraled inward. Theorists also made remarkable progress. In 1965, Roger Penrose proved a theorem showing that the formation of singularities in collapsing objects was not a special feature of idealized, perfectly spherical models. Any sufficiently massive collapsing object would inevitably form a singularity. The mathematics of general relativity guaranteed it. You couldn't escape the singularity by making the collapse slightly irregular or asymmetric. It would form regardless. Stephen Hawking extended Penrose's work and proved that singularities were generic features of general relativity in another context as well. If you run the expansion of the universe backward in time using Einstein's equations, you inevitably reach a singularity at the beginning. The Big Bang was itself a singularity, a moment of infinite density and infinite spacetime curvature where time itself began. General relativity predicted both the future singularities inside black holes and the past singularity at the origin of the universe. These singularities were profoundly troubling. They were places where the equations of general relativity broke down completely, where the mathematical quantities describing the curvature of space-time became infinite and meaningless. They were places where physics stopped working, where the theory told you that it couldn't tell you anything more. Most physicists believed that singularities indicated not a genuine physical reality, but a failure of the theory, a sign that general relativity was incomplete and needed to be replaced by something more fundamental at extreme scales. That something more fundamental, everyone agreed, would have to be a quantum theory of gravity. But developing such a theory would prove to be the hardest problem in theoretical physics. To understand why quantum gravity is so hard, you need to understand what quantum mechanics is and why it conflicts so deeply with general relativity. Quantum mechanics is a theory of physics at the smallest scales, the theory that describes how electrons and photons and quarks and all the other fundamental particles behave. It was developed in the 1920s by a remarkable generation of physicists including Bohr, Heisenberg, Schrödinger, Dirac, Pauli and Born, and it immediately revealed that the microscopic world operates on completely different principles from anything that had come before. In quantum mechanics, particles don't have definite positions and velocities at the same time. The more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. This is Heisenberg's uncertainty principle, and it's not just a statement about the limits of measurement, it's a statement about the nature of reality. Particles genuinely don't have definite positions and velocities simultaneously. They exist in superpositions of many possible states at once, with probabilities associated with each state. When you make a measurement, the superposition collapses to a definite value, but which value you get is fundamentally uncertain. You can only calculate probabilities. This probabilistic, uncertain, superposition-based picture of reality is completely at odds with general relativity's treatment of space-time. In general relativity, space-time is a smooth, deterministic, classical entity. The geometry of space-time at every point is precisely defined by the distribution of mass and energy. There is no uncertainty, no superposition, no probability. The curvature of space-time at a point is a definite number, computable in principle to arbitrary precision given the initial conditions. When physicists tried to apply the methods of quantum mechanics to gravity, to quantize general relativity, the way they had quantized electromagnetism and the other forces, they ran into immediate and severe mathematical problems. The calculations produced infinite answers everywhere, infinities that couldn't be removed by the standard techniques that worked for other forces. The theory was what physicists call non-renormalizable, meaning you couldn't tame the infinities systematically. General relativity resisted quantization at every turn. Meanwhile, the other three fundamental forces of nature, electromagnetism and the strong and weak nuclear forces, were successfully incorporated into a quantum framework during the second half of the 20th century. This framework is called the Standard Model of Particle Physics, and it's one of the most successful theories ever developed. It describes all known particles and their interactions, except gravity, with breathtaking precision. The predictions of the Standard Model have been tested against experiments to better than 10 decimal places in some cases. It's a triumph of human intellect and experimental ingenuity, but the Standard Model has no place for gravity. Gravity simply doesn't fit into the quantum framework in any natural way. Every other force is mediated by particles. Electromagnetism is carried by photons. The strong nuclear force is carried by gluons. The weak nuclear force is carried by W and Z bosons. These particles are all described within the Standard Model. But the hypothetical particle that would carry the gravitational force, the graviton, cannot be incorporated into the Standard Model without the theory producing infinite, meaningless answers. This is the central problem of theoretical physics. We have two extraordinarily successful theories. General relativity works perfectly at large scales, from planets to galaxies to the entire observable universe. Quantum mechanics and the Standard Model work perfectly at small scales, from atoms to subatomic particles to the interactions studied in particle accelerators. But these two theories cannot both be correct in their current forms, because they make fundamentally incompatible assumptions about the nature of reality and about the nature of space-time. The conflict becomes most acute in situations where both gravity and quantum effects are important simultaneously. Inside black holes, where matter has been compressed to extreme densities, both general relativity's description of curved spacetime and quantum mechanics' description of matter at small scales should be relevant. At the Big Bang singularity, where the entire universe was compressed to infinite density, both theories should apply. In these extreme environments, we need a quantum theory of gravity, and we don't have one. Stephen Hawking brought this conflict into sharp focus in 1974 with a remarkable discovery. He showed that black holes, which by classical general relativity should be completely black and absorb everything without emitting anything, actually emit radiation when quantum effects are taken into account. This discovery, now called Hawking radiation, arose from combining the principles of quantum mechanics with the space-time geometry of black holes in a careful calculation. Here's the essence of the argument. Quantum mechanics tells us that empty space is not truly empty. It's filled with what physicists call vacuum fluctuations, pairs of particles and antiparticles that pop into existence spontaneously, exist for the briefest possible moment, and then annihilate each other. This happens everywhere, all the time, throughout all of space. The particles exist only for the brief time allowed by Heisenberg's uncertainty principle, borrowing energy from the vacuum and then returning it when they annihilate. Normally, this process has no macroscopic effects. The virtual particles appear and vanish so quickly that they can't influence anything we can directly observe. But near the event horizon of a black hole, something different can happen. Imagine a pair of virtual particles appearing right at the event horizon. One particle finds itself just inside the horizon, the other just outside. In normal empty space, they would annihilate almost immediately. But the particle inside the horizon is pulled inexorably inward by the black hole's gravity. It cannot reach the particle outside to annihilate with it. The particle outside the horizon, having lost its partner, is no longer virtual. It becomes a real particle. It escapes from the vicinity of the black hole and propagates off to infinity. From the perspective of a distant observer, it looks like the black hole has emitted a particle. But where did the energy for this real particle come from? The particle that fell into the black hole actually carried negative energy from the perspective of an observer outside the horizon, a counterintuitive consequence of the geometry of space-time near an event horizon. By falling in, it reduced the mass of the black hole. The escaping particle carried positive energy, and the total energy was conserved, but the black hole's mass decreased. Over time, as this process continued, the black hole would slowly lose mass and eventually evaporate completely. This was a stunning result. Black holes were not eternal. They would slowly evaporate, losing mass at a rate inversely proportional to their mass squared. Large black holes evaporate very slowly. A black hole with the mass of the Sun would take about 10 to the power of 67 years to completely evaporate, which is incomprehensibly longer than the current age of the universe. But smaller black holes evaporate faster, and as a black hole evaporates, it gets smaller and hotter, and its evaporation accelerates. The final moments of a black hole's evaporation would be a burst of high-energy radiation. Hawking radiation was a profound discovery, but it came with an attached problem that has haunted physics ever since. The information paradox. The radiation emitted by an evaporating black hole is thermal, meaning it's essentially random. It's characterized only by a temperature, and it carries no information about what fell into the black hole to create it. A black hole formed from the collapse of hydrogen gas, and a black hole formed from the collapse of a library full of books would emit identical Hawking radiation. The specific information contained in the books, the precise quantum state of every molecule of paper and ink, would apparently be lost forever when the black hole evaporated. This seems to violate one of the most fundamental principles of quantum mechanics. Quantum mechanics is a unitary theory, meaning that quantum processes are reversible in principle. If you know the quantum state of a system at one time, you can calculate its state at any other time, past or future. Information is never destroyed. It might be scrambled into incredibly complex forms, spread among billions of particles in patterns that would take the lifetime of the universe to decode, but it's always there in principle. The quantum state of the system at one time contains complete information about its state at any other time. But if Hawking radiation is truly thermal and carries no information, then when a black hole evaporates, the information about what fell in is gone, not just scrambled, gone. The quantum state of the system cannot be used to reconstruct the initial state. Unitarity is violated. This is a direct contradiction between general relativity, which predicts thermal Hawking radiation, and quantum mechanics, which says information cannot be destroyed. For decades, physicists argued about whether information really is destroyed in black holes. Hawking himself initially argued that quantum mechanics simply broke down in extreme gravitational fields and unitarity failed. Others, including Leonard Susskind and Gerard Hooft, argued passionately that information must be preserved, that we were missing something important about how it escapes in Hawking radiation. The debate was so fierce that Susskind wrote a book about it called The Black Hole War, describing his decades-long intellectual battle with Hawking over the question. In recent years, remarkable progress has been made on this problem, progress that points toward a resolution, though the full picture is still being worked out. The key developments involve the holographic principle, entanglement entropy, and what physicists call quantum extremal surfaces and islands. The holographic principle emerged from thinking about black hole thermodynamics. In the early 1970s, Jacob Bekenstein realized that black holes must have entropy, a measure of information or disorder, proportional to the area of their event horizon, not their volume. This was surprising. For ordinary objects, entropy is proportional to volume. A bigger box can contain more information, but for black holes, it's the surface area that matters. A black hole with twice the radius has 4 times the entropy. Hawking confirmed this by showing that the area of a black hole's event horizon never decreases in classical general relativity. In analogy with the second law of thermodynamics, which says entropy never decreases. And with Hawking radiation, he could assign a definite temperature to a black hole and show that it radiated like a perfect black body at that temperature, with the temperature inversely proportional to the black hole's mass. The fact that entropy scales with area rather than volume has profound implications. It suggests that in some sense, the information content of a volume of space is determined by its boundary rather than its interior. This is deeply counterintuitive. We normally think information is stored throughout a volume, distributed among all the objects and particles within that volume. But black hole thermodynamics suggests that somehow all the information in a volume can be encoded on its surface. This idea was elevated to a general principle by Gerard Hooft and Leonard Susskind in the 1990s. The holographic principle says that any region of space can be described completely by information living on its boundary. The three-dimensional world we experience might be, in some deep sense, a hologram with the true information encoded on a two-dimensional surface. Just as a flat hologram can encode a three-dimensional image, a two-dimensional surface might encode all the physics of a three-dimensional volume. The holographic principle found its most precise and concrete realization in what's called the ADS-CFT correspondence, discovered by Juan Maldacena in 1997. ADS stands for anti-de Sitter space, a particular type of spacetime with a negative cosmological constant that curves slightly differently from our universe. CFT stands for conformal field theory, a specific type of quantum field theory without gravity. The correspondence says that a theory of quantum gravity in an ADS spacetime is exactly equivalent to a CFT living on the boundary of that spacetime. The two theories are mathematically identical, just described in different language. This is remarkable. It says that a theory of gravity in some spacetime can be completely described by a theory without gravity on the boundary of that spacetime. Gravity, and with it spacetime itself, emerges from the boundary theory. The geometry of spacetime, the very fabric of space and time, is not fundamental. It emerges from the quantum entanglement structure of the boundary theory. This gives us a new way to think about the information paradox. In the boundary theory, which is a standard quantum field theory, unitarity is preserved by construction. Information is never destroyed. Processes are always reversible in principle. So, if the bulk gravity theory is equivalent to the boundary theory, information must also be preserved in the gravity theory. The information that falls into a black hole must somehow be encoded in the Hawking radiation that comes out. But how? The Hawking radiation looks thermal. How can it carry information? The answer came from thinking carefully about quantum entanglement and entropy. When particles fall into a black hole, they become entangled with the particles that escape as Hawking radiation. As the black hole evaporates, more and more entanglement is built up between the interior and the exterior. After a certain time called the Page time, named after physicist Don Page, who first calculated it, the entropy of the radiation starts to decrease rather than increase, because the escaping particles are becoming more and more correlated with each other through their shared entanglement with the interior. Recent work, particularly papers published in 2019 and 2020 by several groups working independently, showed that when you calculate the entropy of Hawking radiation carefully, accounting for a region inside the black hole that physicists call an island, you get a Page curve that rises and then falls, exactly as unitarity requires. The island is a region inside the event horizon that is somehow connected to the exterior radiation through quantum entanglement, and including it in the entropy calculation changes the result dramatically. This work represents the most significant progress on the information paradox in decades. Most physicists working in quantum gravity now believe that information is preserved in black hole evaporation, and that the mechanism involves subtle quantum entanglement effects that are not captured by Hawking's original semi-classical calculation. But the full picture is still being worked out. Exactly how the information is encoded in the radiation, whether the island picture can be derived from first principles rather than just proposed as an ansatz, and what all of this implies for our understanding of space-time at the quantum level, these questions remain active areas of research. What we know is this: the information paradox, which seemed like an irreconcilable conflict between quantum mechanics and general relativity, is leading us toward a new understanding of space-time. The space-time inside a black hole is not as isolated from the exterior as classical general relativity suggests. Quantum entanglement connects regions of space-time that seem causally disconnected, and this suggests that space-time geometry is not the fundamental thing. The fundamental thing is quantum information, and geometry emerges from it. This brings us to the deepest question of all. What is space-time made of? This question drives the search for a quantum theory of gravity, and there are multiple competing proposals, each with its own strengths and weaknesses. The first major approach is string theory. String theory is the most developed and most studied candidate for a quantum theory of gravity, and it has occupied the minds of hundreds of brilliant physicists for more than 4 decades. The basic idea is deceptively simple. What if the fundamental objects in nature are not point particles, but tiny, one-dimensional vibrating strings? Different vibrational modes of these strings correspond to different particles. An electron is one vibration, a photon is another vibration, a quark is yet another, and crucially, one particular vibration corresponds to the graviton, the particle that would carry the gravitational force. This is the key to why string theory incorporates gravity naturally. In every previous attempt to quantize gravity, treating the graviton as a point particle led to uncontrollable infinities in the calculations. But in string theory, the graviton is an extended object, a vibrating string, and this extended nature softens the interactions at short distances and tames the infinities. String theory is, as far as we know, mathematically consistent, at least in certain formulations. This is a major achievement because no other approach to quantum gravity has achieved this, but string theory comes with baggage. To be mathematically consistent, it requires extra dimensions of space beyond the 3 we observe. The original formulation required 26 dimensions. Superstring theory, which incorporates supersymmetry, requires 10 dimensions, 9 of space and 1 of time. M theory, the currently preferred framework that unifies several apparently different string theories, requires 11 dimensions, 10 of space and 1 of time. Where are these extra dimensions? The standard answer is that they're compactified, curled up into tiny spaces so small we can't observe them directly. The extra dimensions might form complicated geometric shapes at scales near the Planck length, about 10 to the power of minus 35 meters, far too small for any current experiment to probe. The shape of these extra dimensions determines the low-energy physics we observe, including the masses of particles and the strengths of forces. Different shapes give different physics, and this is where string theory runs into a profound problem. There are an enormous number of ways to compactify the extra dimensions, each giving a different 4-dimensional universe with different physics. Current estimates suggest there might be as many as 10 to the power of 500 different possible string theory vacua, each describing a different universe with different particles, different forces, different constants of nature. This landscape of possibilities has no obvious physical principle to select among them. No reason to think our universe corresponds to any particular one. Some physicists have responded to the landscape by invoking the anthropic principle and the multiverse. Perhaps all 10 to the 500 vacua are realized, each in its own separate universe in a vast multiverse. We observe the particular universe we do because it's one of the rare ones with physical constants that allow the formation of stars, planets, and intelligent observers. This is anthropic reasoning, and many physicists find it deeply unsatisfying. It seems to abandon the goal of explaining why the laws of nature have the particular form they do, replacing explanation with selection. You can't predict anything from the landscape, because any observation is consistent with some choice of vacuum. String theory also predicts supersymmetry, a symmetry that relates particles of different spin types. Every known particle should have a supersymmetric partner of different spin. Electrons have selectrons, quarks have squarks, photons have photinos. Supersymmetry was one of the most compelling predictions of string theory because it was also motivated by other considerations in particle physics, and because it would naturally solve some puzzling aspects of the Standard Model. The Large Hadron Collider at CERN was specifically designed in part to search for supersymmetric particles. It would have been able to detect them if they existed at the energy scales many physicists expected. But the LHC has found no supersymmetric particles. This doesn't definitively rule out supersymmetry, since the particles could be heavier than the LHC can produce, but it's a significant blow to the most natural versions of the theory. Without experimental confirmation, string theory remains a mathematical framework of great beauty and depth, but uncertain connection to physical reality. Thousands of papers have been written about it. Great mathematical discoveries have been made in the course of studying it, and insights from string theory have illuminated problems in quantum field theory and condensed matter physics. But whether it's the correct description of nature at the Planck scale remains unknown and possibly unknowable with current technology. The second major approach to quantum gravity is loop quantum gravity, where string theory attempts to build a quantum theory by starting from the successes of quantum field theory and incorporating gravity. Loop quantum gravity starts from the success of general relativity and attempts to quantize it directly. The basic idea is to take the mathematics of general relativity and apply the standard procedures of quantization, turning classical fields into quantum operators, imposing commutation relations, and solving the resulting equations. The difference from previous failed attempts is in the choice of variables used to describe the gravitational field. Loop quantum gravity uses variables called Ashtekar variables, after Abe Ashtekar, who introduced them in the 1980s, and these variables turn out to make the equations of quantum gravity much more tractable. When you apply quantum mechanics to gravity using these variables, you find that the geometry of space is not continuous, it's discrete. Space is made up of fundamental units, quanta of space, connected to each other in a network called a spin network. Area and volume are not continuous quantities, but come in discrete multiples of fundamental units given by the Planck length squared and the Planck length cubed respectively. This discreteness of space is a profound consequence. It suggests that at the most fundamental level, space is not the smooth continuum of general relativity, but something more like a very fine graph or lattice, with nodes representing quanta of space and edges representing the connections between them. The geometry of space-time, the distances and curvatures that we measure at everyday scales, emerge from the combinatorial structure of this graph. One of the most attractive features of loop quantum gravity is that it resolves the singularities that appear in classical general relativity. Because space is discrete and has a minimum volume, matter cannot be compressed to a true singularity. Instead of collapsing to infinite density at the center of a black hole or at the Big Bang, matter reaches a maximum density determined by the Planck density, about 10 to the power of 96 kilograms per cubic meter, and then quantum effects prevent further collapse. In loop quantum cosmology, the Big Bang singularity is replaced by a big bounce, a moment of maximum density from which the universe expands after having previously contracted from a previous phase of expansion. But loop quantum gravity has its own serious problems. It's extraordinarily difficult to extract concrete predictions from the theory. The equations are hard to solve even numerically. It's not clear how matter fields, the particles and forces of the standard model, fit into the framework. And the theory hasn't yet been shown to reproduce general relativity in the appropriate limit, meaning that when quantum effects are negligible, the theory should reduce to Einstein's equations. But demonstrating this rigorously has proved very difficult. There's also the question of Lorentz invariance. Special relativity says that the laws of physics are the same for all observers moving at constant velocities. And this symmetry, called Lorentz invariance, is experimentally verified to extraordinary precision. But in loop quantum gravity, the discrete structure of space might break Lorentz invariance at the Planck scale. Whether the theory is fully Lorentz invariant is still being debated, and experiments searching for tiny violations of Lorentz symmetry have so far found nothing. Beyond string theory and loop quantum gravity, there are other approaches, each capturing some aspects of what a quantum theory of gravity should look like, without any one of them being fully satisfying. Causal dynamical triangulations build spacetime out of tiny simplices, the higher dimensional analogues of triangles, and shows that a sensible four-dimensional spacetime geometry can emerge from this combinatorial structure. Causal set theory proposes that the fundamental structure of spacetime is a partially ordered set of discrete events, with the causal relationships between events being the primary ingredient and geometry emerging from those relationships. And then there's the approach suggested by the ADS-CFT correspondence and the information paradox work, which might be the most radical. This approach suggests that space-time is not fundamental at all. It's emergent. The true description of nature involves quantum information, entanglement between degrees of freedom in some more fundamental structure, and space-time geometry emerges from the pattern of entanglement. This is related to ideas developed by Mark van Raamsdonk and others in the 2010s. Van Raamsdonk proposed that the connectivity of space-time, the fact that different regions of space are connected to each other and can influence each other, is a consequence of quantum entanglement between degrees of freedom describing those regions. Take away the entanglement, and space-time falls apart, splits into disconnected pieces. Increase the entanglement, and space-time becomes more connected. The geometry of space-time, the distances between points, the curvature, all of it is encoded in the pattern of quantum entanglement. This view is supported by calculations in ADS-CFT. In that framework, the geometry of the bulk spacetime can be reconstructed from the entanglement structure of the boundary theory. Regions of the bulk that are near each other correspond to regions of the boundary that are highly entangled. Regions of the bulk that are far apart correspond to regions of the boundary with little entanglement. Distance in spacetime is a measure of quantum entanglement. Spacetime is woven from entanglement. If this is right, it has profound implications. Spacetime is not the fundamental stuff of the universe. Quantum information is. Space and time are useful descriptions that emerge at large scales from something more fundamental, just as temperature and pressure are useful descriptions that emerge from the collective behavior of vast numbers of atoms, even though there's no single atom that has a temperature or pressure. Just as the smoothness of a liquid emerges from the collective behavior of discrete molecules, even though no individual molecule is liquid, Space and time might emerge from the collective behavior of quantum degrees of freedom that are not themselves spatial or temporal. This idea, if correct, would represent the most profound revolution in our understanding of nature since quantum mechanics was developed a century ago. It would mean that the stage on which all of physics plays out, space and time, the very framework in which we describe the universe, is not part of the fundamental description. It's an approximation, a convenient description that breaks down at small enough scales. At the most fundamental level, there might be no space, no time, no here and now, no before and after. Only quantum information, and the world we experience would be an elaborate, emergent phenomenon arising from that information. While physicists wrestle with these deep theoretical questions, observations continue to provide new data about space-time in its most extreme forms. The gravitational wave detectors, LIGO in the United States, Virgo in Italy, and Kagra in Japan, have detected dozens of space-time warping events since their first detection in 2015. Each detection is a direct observation of space-time in motion, ripples, propagating through the fabric at the speed of light. The signals detected so far have included mergers of binary black holes of various masses, mergers of binary neutron stars, and possibly mergers of a black hole with a neutron star. Each event provides a test of general relativity in the strong field, highly dynamic regime that was previously inaccessible. So far, every measurement has been consistent with Einstein's equations. No deviation from general relativity has been detected, but the precision of the tests is improving with each generation of detectors, and future detectors like the planned space-based LISA mission and next-generation ground-based detectors like Einstein Telescope and Cosmic Explorer will be sensitive to far weaker signals from far more distant events. These future detectors might be able to observe gravitational waves from the Big Bang itself, primordial ripples from the earliest moments of the universe that were generated during inflation or other early universe processes. Such observations would give us a direct window into the first fraction of a second after the Big Bang, a window that electromagnetic observations cannot provide because the universe was opaque to light until 380,000 years after the Big Bang. The Event Horizon Telescope, which produced the first images of black holes in 2019 and 2022, is also continuing its work. The next generation Event Horizon Telescope will have greater sensitivity and resolution, allowing it to track how the material around the black hole at the center of our galaxy moves over time, providing detailed tests of general relativity in the strong field regime near a supermassive black hole. It might even be possible to observe gravitational effects predicted by quantum gravity theories, such as subtle deviations from the classical prediction for the size and shape of the shadow, if such deviations are large enough to detect. Meanwhile, cosmological observations are providing increasingly precise measurements of the large-scale structure and evolution of the universe. The Planck satellite's measurements of the cosmic microwave background have given us the most precise measurements yet of the universe's age, composition, and geometry. Future missions like the Euclid Telescope and the Vera Rubin Observatory will map the distribution of galaxies across enormous volumes of space, testing models of dark matter, dark energy, and the large-scale structure predicted by inflation. And the Big Bang dark energy itself remains one of the most mysterious aspects of the universe. Discovered in 1998 through observations of distant supernovae, dark energy is the name for whatever is causing the expansion of the universe to accelerate. It makes up about 68% of the total energy content of the universe, but has never been directly detected or identified. The simplest explanation is the cosmological constant, a constant energy density associated with empty space itself, which Einstein actually introduced into his equations in 1917 before abandoning it when Hubble discovered the expansion of the universe. Einstein called it his greatest blunder, but it turns out something like it is really there. The cosmological constant poses its own deep mystery. Quantum field theory predicts that the vacuum of space should have an enormous energy density from quantum fluctuations. The prediction disagrees with the observed value of the cosmological constant by a factor of about 10 to the power of 120, the largest discrepancy between theory and observation in all of physics. Something cancels the vast majority of the predicted vacuum energy, leaving only a tiny remnant, and we have absolutely no idea what that something is. This is called the cosmological constant problem, and it's one of the most embarrassing unresolved problems in theoretical physics. Understanding dark energy and the cosmological constant will likely require the same quantum theory of gravity that we need to understand black holes and the Big Bang. They are different manifestations of the same deep ignorance about quantum gravity and the nature of space-time at the fundamental level. There's also the question of dark matter, which makes up about 27% of the universe's energy content, but has never been directly detected despite decades of searching. Dark matter is inferred from its gravitational effects. It affects the rotation curves of galaxies, the bending of light by galaxy clusters, and the large-scale structure of the universe. But we don't know what it is. It doesn't emit, absorb, or reflect electromagnetic radiation. It interacts only through gravity and possibly through the weak nuclear force. The leading candidates are new types of particles beyond the standard model, such as weakly interacting massive particles or axions, but none have been found. It's possible that understanding dark matter will require a modification of gravity at galactic scales, which would itself point toward new physics beyond general relativity. All of these mysteries, quantum gravity, the information paradox, dark matter, dark energy, the cosmological constant problem, the origin of the universe converge on a single point. We don't understand what space-time is at its most fundamental level. We have a theory, general relativity, that describes space-time's behavior with extraordinary accuracy across an enormous range of scales. But the theory breaks down at singularities, it conflicts with quantum mechanics, and it offers no explanation for the fundamental nature of the fabric it describes. The search for a quantum theory of gravity is the search for a deeper understanding of space-time. It's the search for the atoms of space and time, for the fundamental building blocks from which the stage of the universe is constructed. It's one of the greatest intellectual adventures in human history, and it's happening right now in physics departments and theoretical institutes around the world as mathematicians and physicists develop new ideas and test them against the constraints of experiment and observation. There's something philosophically profound about the situation we find ourselves in. We are creatures made of matter, living on a planet orbiting a star, in a galaxy floating in a universe that has been expanding for 13.8 billion years. We evolved to navigate a world of trees and predators and fruit, where the relevant scales are meters and seconds, where the effects of relativity are completely negligible and quantum effects are invisible. And yet, through the power of mathematics and reasoning and experimental ingenuity, We have managed to understand the behavior of space-time to a degree that still astonishes. We have detected gravitational waves from collisions of black holes 1 billion light-years away. We have photographed the shadow of a black hole 6.5 billion times the mass of the Sun. We have mapped the temperature variations in light left over from an era when the universe was 380,000 years old. We have used the equations of general relativity to navigate satellites to within meters of their intended orbits, and yet we still don't know what space-time is. We have the equations, we have the predictions, we have the experimental confirmations, but the underlying reality, the thing that the equations are describing, remains mysterious. In a deep sense, we are like ancient astronomers who knew how to predict the motions of the planets with great accuracy using the Ptolemaic system of epicycles, who had detailed tables of where each planet would be on any given night, but who didn't know why those predictions worked, didn't know that the planets were massive bodies orbiting a star due to gravity. We can calculate, we can predict, but we don't fully understand the resolution of this mystery when it comes. Might come from mathematics, from some new geometric framework that unifies quantum mechanics and general relativity in a way we haven't imagined. It might come from experiment, from observations of gravitational waves, or the cosmic microwave background, or the behavior of matter in extreme environments that reveal deviations from current theories. It might come from theoretical insights about the relationship between information and geometry, building on the connections that the ADS-CFT correspondence and the information paradox work have revealed. It might come from somewhere completely unexpected, from a direction no one is currently looking. Great scientific revolutions are rarely anticipated. Newton didn't predict that Einstein would come along and show that his equations were approximations to a deeper theory. Einstein didn't predict that quantum mechanics would reveal a world of probability and superposition so alien to his own intuitions that he never fully accepted it. The people who discovered quantum mechanics didn't predict that it would lead to transistors and lasers and computers. The discovery of general relativity didn't obviously suggest GPS satellites. The history of physics is full of surprises, of unexpected connections and revolutions that seemed impossible before they happened. The solution to the mystery of space-time might come from an entirely new way of thinking, a conceptual revolution comparable to Einstein's realization that space and time are flexible rather than absolute, or to the realization that quantum mechanics describes not a definite reality, but a probability distribution over possible realities. It might require letting go of assumptions so deep we don't even know we're making them. It might require accepting that what we call space-time is as different from the true fundamental description of nature as a water wave is from the water molecules that make it up. What we know is this: space-time is real. You are embedded in it right now. The chair you're sitting in, the air you're breathing, the light reaching your eyes from the screen in front of you, all of it exists in space-time, woven into the four-dimensional fabric that Einstein described. The forces that hold atoms together, the movements of planets, the expansion of the universe, the radiation from distant black holes, all of it happens in and through space-time. It's the stage on which all of physics plays out, the most fundamental arena of physical reality. And yet we don't know what it is. We can describe it. We can calculate with it. We can measure its curvature and detect its waves. But its fundamental nature, what it's made of at the deepest level, whether it's truly fundamental or emergent from something else, what happens to it inside black holes, And at the Big Bang, where the equations break down, these questions remain open. They are the frontier of human knowledge, the place where the map runs out and the unexplored territory begins. The physicists working on these problems today are doing what physicists have always done. They're asking the deepest questions they can formulate about the nature of reality, developing mathematical frameworks to describe possible answers, and testing those frameworks against the rigorous judge of experiment and observation. They're standing at the edge of the known, looking out into the dark and trying to see what's there. Some of them will spend their entire careers on this problem without solving it. Others will make partial progress, developing new tools and new frameworks that future generations will build on. And perhaps somewhere, in some physics department or theoretical institute, or even in some unexpected mind outside academia, someone is already developing the key idea that will unlock the mystery. Perhaps the equation that describes the true fundamental nature of space-time is already being written down, and we just don't know it yet. This is what science is. Not a collection of settled answers, but a process, a perpetual reaching toward deeper understanding, always discovering that the universe is stranger and more wonderful than we thought. Always finding that behind the answers we've found lie deeper questions we haven't yet imagined. Space-time is one of those deeper questions, the one that sits at the very foundation of our understanding of physical reality. We use it every day. We navigate by it. We've photographed it. We've detected its waves. And we still don't know what it is. And that is not a failure. That is the most exciting thing in all of science, because somewhere behind that mystery, behind that gap between what we can calculate and what we can understand, lies the next great revolution in human knowledge. The revelation that will change how we think about space and time and reality itself, that will open doors we can't see yet, and that will leave future generations looking back at us the way we look back at the pre-Einsteinian world, marveling at how much we didn't know about something we were so sure we understood. The mystery of space-time is real. The quest to solve it is ongoing, and the adventure, the deepest adventure of the human mind, has never been more exciting than it is right now. That's where we are. And that's where the story is still being written.